The year is 2050. A child wakes up in a pressurized dome, looks through triple-paned glass at a rust-colored sunrise, and asks their parent a question no human has ever asked before. What's Earth like? This isn't fantasy. The foundation is already being laid. SpaceX isn't just planning to visit Mars. They're engineering humanity's insurance policy. A second home. A backup civilization. 1 million people living, working, and thriving on a planet that's currently a frozen, radiation-soaked wasteland. The rockets exist. The timeline is set. And the most audacious construction project in history has already begun. But here's the part that sounds impossible. Mars won't be colonized by astronauts. It'll be built by an army of robots who arrive decades before the first human ever steps foot on Martian soil. Here's why Mars is different from every other space mission humanity has attempted. The Moon? We planted flags, took samples, and came home. 12 days maximum. Resupply from Earth in 3 days if something broke. Mars is playing a completely different game. The journey alone takes 7 months, one way. Launch windows only open every 26 months when orbital mechanics align. If something critical fails, there's no emergency return. No cavalry coming over the hill. You either fix it with what you have, or you die waiting for a rescue ship that won't arrive for years. And that creates the ultimate engineering paradox. Mars must be self-sustaining from day one. But you can't achieve self-sustainability without infrastructure. No infrastructure exists without construction. And construction requires workers who can survive in an environment with no oxygen, no water, and enough radiation to kill a human in months. So how do you build a city when the builders can't survive long enough to build it? You send the machines first. Picture the Martian surface in 2029. Empty, silent. Then, a streak of fire across the pink sky. The first starship touches, down. No crew, no life support systems, just cargo. The ramp extends, and what rolls out isn't human. It's a fleet of Tesla Optimus robots, their movements precise, their purpose singular. No spacesuits required. No psychological concerns about isolation. Just tireless workers designed for one thing: building the infrastructure that makes human survival possible. Their assignment list reads like a construction contract written by someone insane. First, deploy solar arrays. Miles of photovoltaic panels unfurling across plains that haven't seen movement in 1 billion years. Mars receives 43% less sunlight than Earth, so the arrays need to be massive, fields large enough to be visible from orbit. Next, power storage. Tesla Megapacks, adapted for Martian conditions, creating battery farms that stockpile energy through the day to power operations through the 14-hour nights. Then comes Phase 2, extraction. The robots begin drilling. Not for oil, for water ice, locked beneath the regolith in deposits that satellite imaging has already mapped. Automated mining rigs pull frozen blocks to the surface, where processing units melt, purify, and split the water into hydrogen and oxygen. Rocket fuel, breathable air. The two most valuable commodities on Mars, manufactured on-site from the planet itself. And while some robots mine, others dig. Boring machines, scaled-down versions of technology tested in Vegas and LA, carve tunnels into Martian hillsides, creating the bones of what will become an underground city. The math is staggering. To support 1 million people, SpaceX estimates needing 1,000 Starship flights. Each ship carries 100 tons of cargo. Everything from solar panels to semiconductor manufacturing equipment to bags of freeze-dried seeds. But here's the constraint nobody talks about: Orbital mechanics. Earth and Mars align for optimal transfer windows only once every 26 months. Miss the window, and you wait over 2 years for the next one. So the flights happen in waves, armadas of ships launching in coordinated convoys during brief windows when the planets cooperate. The first cargo missions, likely late this decade, will land the heavy equipment, mining rigs, nuclear reactors, construction drones. The second wave brings redundancy, backup systems for everything, because there's no hardware store 34 million miles away. Then, in the 2030s, the first crewed starship makes the journey. Not colonists, engineers and technicians sent to oversee the transition from robotic construction to human habitation. They'll live in prefabricated modules erected by the robots, breathing recycled air and drinking water extracted by machines, while they activate systems designed to support the thousands who will follow. Building a city on Mars requires solving 3 problems that sound simple until you understand what they actually mean. Problem 1. Radiation. Earth's magnetic field is a shield we take for granted. It deflects cosmic rays and solar radiation that would shred DNA like tissue paper. Mars has no magnetic field. Standing on the surface exposes you to radiation levels that would give you cancer in months, not years. The solution isn't lead walls, too heavy to transport. It's ice. Specifically, 6-foot-thick domes made of water ice excavated from subsurface deposits. The robots shape the blocks, stack them into pressurized shells, and seal them with inflatable membranes on the interior. Water is the perfect radiation shield, abundant on Mars, effective at stopping particles, and when you need more drinking water, you just melt part of your house. Problem 2. Building materials. You can't ship concrete from Earth. The cost per kilogram makes it economically impossible. So Martian construction uses Martian resources. Enter biocrete, a composite material mixing regolith dust with polymer binders and a component nobody wants to discuss at dinner. Organic waste from human habitation. The robots 3D print it, layer by layer, extruding structures that harden in Martian atmospheric conditions. Domes, tunnels, pressurized corridors connecting habitats to greenhouses to manufacturing centers. The architecture isn't beautiful. It's functional, designed for survival first, and aesthetics never. Problem 3. Energy independence. Solar works during Martian day, but nights are brutal. Temperatures plunge to negative 100 degrees Fahrenheit. Batteries help, but they degrade. The long-term answer is nuclear, small modular reactors buried deep in the regolith, generating baseload power 24/7, regardless of weather, dust storms, or seasonal variations. The robots install them in excavated chambers, shielded by meters of Martian soil. Cooling systems use extracted subsurface water. Backup systems have backups. Because on Mars, a power grid failure doesn't mean inconvenience. It means suffocation within hours as life support fails. So what does daily life actually look like for the first Martians? You wake up in a module 20 feet underground. The ceiling glows with LED panels mimicking Earth's daylight cycle. Psychological necessity to prevent depression in an environment where the sun is a distant, weak disk in a butterscotch sky. Your home is sparse. Everything is multifunctional. Beds fold into walls. Tables collapse. Water is recycled so aggressively that every shower you take has been through the filtration system dozens of times. You taste the minerals. You get used to it. Breakfast comes from hydroponic farms in pressurized greenhouses. Lettuce, tomatoes. Potatoes grown under pink LED. Grow lights calibrated to photosynthetic efficiency rather than human vision. Protein comes from insects and lab-grown meat. Livestock require too much water, too much feed, too much space for a colony fighting for every resource. Work happens in tunnels. The Boring Company's network expands constantly, machines carving new corridors while humans oversee manufacturing operations. 3D printers producing replacement parts. Refineries processing regolith into metals. Fabrication labs building electronics from Martian silicon. You never go outside without a suit. Ever. The atmosphere is 0.6% the density of Earth's. Your blood would boil. Your lungs would collapse. Even with the suit, you move carefully. Martian gravity is 38% of Earth's, and missteps can send you tumbling in slow motion into rock formations that will puncture your equipment. But here's what nobody tells you. You adapt. The human body is stunningly resilient. Bone density decreases, but stabilizes. Muscles atrophy, but specialize. Children born here will have skeletons we can't predict. Lighter, optimized for low gravity, possibly unable to ever visit Earth without breaking under their own weight. Everything described so far is engineering. Difficult, yes, but solvable with enough money, time, and robotic labor. The final problem is biological, and we haven't cracked it. Agriculture at scale. Martian regolith isn't soil. It's toxic dust filled with perchlorates, chemicals that destroy your thyroid and contaminate anything grown in it. Washing it out requires water we can't spare. Replacing it with earth soil requires mass we can't launch. Current solutions involve sealed hydroponic systems, but they're energy-intensive and fragile. A contamination event could wipe out months of crops. A power failure kills the grow lights, and everything dies within days. And the psychological impact of eating rehydrated algae paste and vitamin supplements while staring at a dead planet through a window? That breaks people in ways radiation can't. The colony can't sustain 1 million people on hydroponics alone. We need breakthrough crops, genetically modified plants that tolerate perchlorate, thrive in low light, and produce calorie-dense yields in Martian conditions. We need soil microbiomes engineered from scratch. We need agricultural systems that don't exist yet. This is the boss-level problem, the one that determines whether Mars becomes a civilization or a very expensive graveyard with excellent infrastructure. If SpaceX cracks propulsion, Tesla cracks automation, and the Boring Company cracks underground construction, all problems they're already solving, then Mars becomes inevitable. The robots are already in production. The rockets are flying. The engineering challenges have solutions on whiteboards and in CAD software. But here's the question that keeps scientists awake. When the first child is born under a Martian sky, looks up at a blue dot in the darkness, and asks why humanity left its cradle, what do we tell them? Was it survival? Curiosity? Hubris? Maybe it's all three.